Hello and welcome to another session of Recitation for ENGR 330 Fluid Mechanics. And in this session, we'll look at some concepts we covered in Chapter 8 and some problems which are relevant to the concepts we learned. Let's look at problem 4 from Chapter 8 in your textbook. Air at 200 Fahrenheit flows at standard atmospheric pressure in a pipe at a rate of 0.08 pound per second. You're asked to determine the minimum diameter allowed if the flow is to be laminar. So we know that for a laminar flow, at most the Reynolds number can be 2100. Okay, so let's first write that. So Reynolds number can be 2100. Now let's write what would be the Reynolds number. What is the definition? It would be the density of the fluid, the velocity with which the fluid is flowing, times the diameter over the absolute viscosity. So in this we know the fluid, so we can find the density and the viscosity at the temperature 200 F for air. If you go to table B3, you can find mu, which is 4.49 into the 10 to the minus 7 pound second per square feet. Okay, and similarly, you can get density for air at 200 F would be 1.87 into 10 to the negative 3 slugs per cubic feet. You can actually find density in another way if you wanted. You know that it's standard atmospheric pressure, so you can use the ideal gas. So P equals rho RP, okay, and you can find rho from there as well if you wanted. You should get the same density though, either way. Anyway, so this number should be equal to 2100. Okay, so we know the density now, we know the viscosity, we know that we want to find the diameter, but we don't know velocity at this point. But we were given that in a pipe, it flows in a pipe at a rate of 0.08 pound per second. Let's see how we can use that. So we know that Q is V times A, the volumetric flow rate is equal to velocity times the cross-sectional area, or I can write this, gives me V equals Q over A, okay, or I can further write this as 4 times Q over pi D squared, okay. Alright, so now in this case I can put that in the Reynolds number form, so I can write Q equals 2100 times viscosity pi d over 4 times rho, okay, where rho is your density. However, we don't know Q at this point, but what you're given is actually gamma times Q, where gamma is your specific weight, is equals 0.08 pound per second. If you want, you can check the dimensions and it will work out. And gamma is nothing but rho times G. You know rho, you know G, so you can find Q. So Q will be 1.33 cubic feet per second. Okay. So now in the above equation for Q, the only unknown is D, right? So I can substitute that. So that means D will be, if you do the math, it's about 3.35 feet. Okay. So this is how you accomplish doing this problem. Okay, now let's look at another problem. You're given the wall shear stress in a fully developed flow portion of a 12-inch diameter pipe carrying water is 1.85 pound per square feet. You're asked to determine the pressure gradient dou P dou X, where X is in the flow direction, and you're given three scenarios. One is if the pipe is horizontal, the other one is if it is vertical with the flow up, and the third case is if it is vertical with the flow down. What you need to do here is to come up with a formulation which relates the dP dx or dou P dou X and the shear stress at the wall, and also you kind of see that you have to have the inclination of the pipe because of those three conditions. You can go and look at in your book, and the general form is delta P minus gamma L sine theta over L, where L is the length of the pipe, is equal 2 times shear stress over R. Okay, where tau is valid at any R. However, in this problem we are interested in tau wall is what we are given, so we can replace this guy with tau wall. In any event, let's try to rewrite this. I can write this as delta P over L equals 2 tau over R plus gamma sine theta. Okay, so I can do this. I've just simplified it, so I get delta P over L and all of this, and you can see that this guy is nothing but dou P dou X. It's change in pressure over change in X. In this case it will be just L, and this is what we are after. Okay, now what we have to do is just look at each situation. If it is horizontal, theta will be 0, sine theta will be 0. If it is vertical with the flow up, theta will be 90 degrees. If it is vertical with flow down, theta will be negative 90. Okay, based on that, so for part A, theta is 0. So delta P over L is just 2 tau wall at this point over R. If you do the math here, you should get 7.4 units pound per cubic feet. Okay, and similarly for part B, theta will be 90 degrees, right? So delta P over L will be 2 tau wall over R plus gamma sine 90. So if you simplify this, you get this to be 69.8 pound per cubic feet. And part C, it is vertical with flow down, pipe is vertical, so theta is negative 90. Okay, and if you substitute it, delta P over L will be 2 tau wall over R minus gamma, right? And here sine 90 is 1, sine 90 is negative 1, so minus gamma. So we'll get this to be negative 55 pound per cubic feet. Okay, so this is how you accomplish this particular problem. Okay, let's move on to the next problem. So in this, you're given water at 60 Fahrenheit flows through a 6-inch diameter pipe with an average velocity of 15 feet per second. Approximately, what is the height of the largest roughness element allowed if this pipe is to be classified as smooth? So if the pipe has to be classified as smooth, the largest roughness element can be at most the height of the viscous sublayer. Okay, so let's try to represent this. So if I have a pipe here, which is what we are given in the problem, okay, we know that it's 6 inches, and we know that water is what is flowing through it at 15 feet per second. Okay, so if this is your roughness, so epsilon can be at most equals delta S. So we know that if we find delta S, we find the height of the roughness element, or epsilon in this case. Okay, so delta S is what? Okay. Before I write out the formula for delta S, let's go ahead and compute the Reynolds number, which is V times D over mu. So you know the velocity, you know the diameter, make sure you convert it to feet since velocity is in feet per second, and you can find the kinematic viscosity for water from the book, and you should get this to be 6.19 into 10 to the 5. Okay, now let's go ahead and write what delta S is. If it is in the viscous sublayer, right, it's between 0 and 5, the thickness, so you can write this as 5 times nu over u star. Okay, so at this point we know nu, but we don't know u star, but u star is nothing but tau wall over rho, density of the fluid, square root. Okay, now if you look at this, we don't know tau wall. Okay, however, what I can do is I can write tau wall in terms of the pressure gradient, right? In this case, I don't know the length of the pipe, I don't know the pressure gradient, but I know that for a turbulent flow, because you see that your Reynolds number is 6.19 10 to the 5, so it's obviously turbulent flow. So you can get delta P for a turbulent flow is F, the friction factor, L over D times rho V square over 2. So from here, if you simplify it, tau wall will be rho F V square over 8, and if you substitute it in U star, it would be square root of F over 8 times V. Okay, and you can check this math, it's just a simple simplification here. Okay, and then if you substitute that in this delta S, you get 5 times nu over square root of F over 8 times the velocity. So in this, we didn't find F yet, but if you go back to your Moody diagram, we know that it is a smooth pipe, right? So this is where you want to be, and you know the Reynolds number, which is 6.19 into 10 to the minus, sorry, into 10 to the 5. So you go up this line here, approximately touch the smooth line and read off what you get on this horizontal line here in terms of F. Okay, if you do that, you'll get F from figure 8.20. F is 0.0125. Okay, so if you put in all the numbers, and now since we know everything in this equation, we can get delta S to be 1.02 10 to the negative 4 feet, or about 0.33 mm. The reason I wanted to do this is, you see that as we discussed in class, the height of the thickness of the sublayer is really small compared to your diameter of the pipe, which was 6 inches. Okay, so this is how you calculate the delta S in this problem, and this delta S will also be, for this problem situation, it will be the height of the roughness element if the pipe has to be classified as smooth. Okay, alright, now let's move on to the next problem. You're given gasoline flows in a smooth pipe, that means epsilon is 0, of 40 mm diameter at a rate of 0.001 cubic meter per second. That means you're given the volumetric flow rate Q. If it were possible to prevent turbulence from occurring, what would be the ratio of the head loss for the actual turbulent flow compared to that if it were laminar flow? Okay, so we are talking about head losses. So let's go ahead and write what would be the head losses for a turbulent flow. Head losses will be F, friction factor for turbulent flow, times L over D V square over 2G. Okay, and for a laminar flow, it will be F laminar L over D V square over 2G. Okay, okay, so we have to find, since it's a turbulent flow, we would like to know what is the Reynolds number. We already know it's a smooth pipe, and since we have to find the friction factor in a turbulent flow, we have to find the Reynolds number, but we don't know the velocity at this point. But the velocity will be same if it were turbulent and also if it were laminar. Okay, and we can go ahead and use our volumetric flow rate, and if you go ahead and do that, you'll get 0.796 meter per second. Okay, and you can then compute your Reynolds number, which is rho BD over mu. So you can go up to your front of the book, table 1.6, and you can punch in the numbers. You get the Reynolds number as 6.98 into 10 to the 4. Okay, so now we know that it is a smooth pipe, and so it's about somewhere here in terms of Reynolds number, 6.98 into 10 to the 4. So go up vertically onto the smooth line and then go horizontally, and you can see that it's about a number which is close to 0.02, the friction factor. Okay, okay, so now F turbulent will be 0.0912, again from figure 8.20, for Re plus smooth pipe. Okay, so you got the friction factor, and then you know that for a laminar flow, friction factor is just 64 over the Reynolds number. So you can find this easily. So it's about 9.16 into 10 to the negative 4. Now we want to find HL, head losses for a turbulent case, and head losses if it were laminar, right? And if you go back and divide these guys, you see that all the L over D's, V square over 2G's gets cancelled. So all you get remained is F turbulence over F laminar. Okay, so it's F turbulent over F laminar, which we just found out above. So if you do that, you'll get 21. So what that tells you is the head losses in a turbulent flow are 21 times greater than the head losses in a laminar flow. Okay, let's go ahead and look at one final problem, wherein we will also look at the minor losses. Since we talked about in class that the total head losses would be the contribution of the major losses and the minor losses. The major losses are due to the straight pipes due to the viscous effects, whereas in the minor losses are because of the entrance and exit flows, and also due to the fact that you might have to connect these pipes with elbows, valves, what have you. Okay, so water flows from the container as shown. You're asked to determine the loss coefficient needed in this valve right here if the water is to bubble up 3 inches above the outlet pipe. The entrance is slightly rounded. Okay, so we have done these kind of problems before. If you remember in chapter 3, when we applied the Bernoulli equation. However, we realized that that might not be really accurate because we know that in real world losses would occur, so we have to consider the energy equation with the head losses included in there. Let me go ahead and identify some key points here since I'm going to use the energy equation. I'm going to name this point here as 1 and point here as 2 and then top of this flow as 3. Okay, so let's go ahead and write the Bernoulli equation from 2 to 3. So I get P2 over gamma plus B2 square over 2G plus Z2 equals P3 over gamma plus V3 square over 2G plus Z3. Yes, you might be wondering why there are no head losses. The reason is there is no pipe between 2 and 3. Okay, and you can see that P2 is 0, P3 is 0 gauge, right? And V2 is what we are after. V3 is again 0 because it's the top of the fountain. Okay, we know how to do these from before. So all you can get from here is you have a one equation and you have a one unknown, which is the velocity at point 2, which is v2. If we do the math here, we get that to be 4.01 feet per second. Okay, so but our idea is to actually find the loss coefficient in the valve. So we have to somehow incorporate that and come up with an equation. So if I write an energy equation going from 1 to 3, I capture all the valve and the elbows and the entrance effects. Okay, so let's go ahead and do that. So P1 over gamma plus V1 square over 2G plus Z1 equals P3 over gamma plus V3 square over 2G plus Z, Z3. However, we have to incorporate losses now, right? So it would be plus. So you have the major losses throughout the entire length of the pipe, right? Which is F times L over T, V square over 2G, plus you have all the minor losses, and I'm gonna show you what this is. It's sigma KL because we have several components. I'm going to identify what sigma KL is, but this is your minor head loss. Okay, so this is your major, this is your minor. Okay, H major, H minor, and this is total head loss. Okay, so in this equation, P1 is 0, V1 is 0, V3 is 0, P3 is 0. So you can see that at this point we don't know F, but we can find it. And let me write what sigma KL is. So sigma KL, you have an entrance effect. It's slightly rounded, so you can find the loss coefficient there. You have an elbow here, an elbow here, so you can find the loss coefficient there. You're given that it's threaded fitting, so we can find that, and this is the unknown, okay, the loss coefficient for the valve. So the way you find these is basically in this table here, okay, table 8.2. So for elbows, 90-degree angle and threaded, the loss coefficient is 1.5. Okay, so it would be 2 times 1.5 because there are two elbows, plus, so let me write this, elbows, 90-degree threaded elbows, plus you have the loss coefficient in the valve, plus zero point 0.2 where this is slightly rounded entrance. Okay, okay, and this you can find in the figure in the book. You can, where they talk about the entrance flows, you can find this particular value. So you see that in this equation at this point we have not determined F, okay, but you can kind of see that in this whole equation this would be your unknown, and let's try to find F now, okay, which we should do because we know the velocity, we can find the Reynolds number, right? So let's go ahead and find the Reynolds number. So the Reynolds number is V times D over nu, right? You know it's water, so you can find nu. So Reynolds number is 13,800. Okay. Okay. Um, if you want to find the friction factor, you have to find the roughness as well, since it's not a smooth pipe. You're given that it is a 1/2 inch diameter galvanized iron pipe with threaded fittings. Okay, so it's galvanized iron pipe. So the way you can find information about that is you go to table 8.1. It will give you the equivalent roughness. So for galvanized iron, the equivalent roughness E or epsilon is 0.0005 feet. Okay, so I can find that there. So epsilon over D is half an inch, so make sure you convert to feet. So it will be about 0.012. So these two guys will then give you F from figure 8.20. F will be 0.043. Okay. Okay. So now that you have F, let's go back to our equation. So you can see that I found F Z3 minus Z1. Okay, you should be able to do it by now. Just look at the figure here and you'll find the what exactly is Z3 minus Z1. And the length of the pipe is nothing but 18 inches here, 32 inches here, and about 2 inch here, so it's about 52 inches. So that's your length of the total length of the pipe. Okay, so I can do that. I know the diameter of the pipe, it's half an inch. Okay, and I know the velocity which we computed earlier. So I know everything. The only unknown is KL valve. Okay, so if I put that KL valve turns out to be 5.7. Okay, okay, so all that it had was you to apply the energy equation, and you just included head losses now. If you didn't cover head losses, like in chapter 3, you wouldn't have done this, but now we realize that it's very important and we have done it. It's just a couple of formulae, but this is how we do these problems. Alright, so this concludes the session for chapter 8. Looking forward to talking to you again. Good luck for the rest of the semester.